Before we get started on networks, we need to get familiar with some of the terminology. Networks are used to show how things are connected. A network is a structure that shows the physical connection or relationship between things of interest. They can be used to help solve problems in many different industries. In mathematics, networks are often referred to as graphs, and the area of mathematics concerning the study of graphs is called graph theory. In this video, we'll look at what a network is, the application of networks, what graph theory is, specific terminology regarding networks, types of networks, and finally what an algorithm is. A network is a type of graph that is used to show the relationship between things or how they are connected. They usually represent real-life situations. The theory of networks was developed centuries ago, but the application of theoretical ideas is relatively recent. Having only been studied in depth since the Second World War, networks are used in maths to study how things are connected. Networks can represent all sorts of systems in the real world, including but not limited to internet connections, relationships, or even traffic flow. Networks are used by businesses and governments around the world to find optimal solutions to practical problems. The solution may be the thing that costs the least, that takes the least time, or requires the smallest amount of material. Some examples of typical networks include vehicle or distribution motorways, rail, electricity grids, water circuits. In the top left-hand corner here, I have a picture of the London Underground network. We also look at networks for socio-economic reasons, including trade, politics, friendships. On the right-hand side of the screen, I have an example of a social media network with connections between people. We also use networks for spatial temporal reasons, including timetables, zonal maps, chemical structures. On the bottom left, I have an example of a Qantas Airways destination flight map. Almost any set of complex relationships between variables can be represented using a network. If you want to analyze networks, we need a way of describing them and analyzing them mathematically. We do this by converting networks into graphs to find how to efficiently move around the networks, how networks are broken down, if a network can be improved by adding additional links, and finally, how things spread around networks. Like most areas of mathematics, networks have their own set of terminology that is important to understand before we can analyze them. A graph of a network is a structure which shows the physical connection or relationship between things of interest. A graph is a series of points or dots that may or may not be connected to each other by lines. Here I have three basic examples of network graphs. The points on the network are known as nodes or vertices. Colored blue on the graphs here. The number of vertices a graph has is the order of the graph. The degree of a vertex is determined by how many edges join it to other vertices. The connections or relationships between the nodes or vertices are colored white here. In the first example, the network has 4 nodes or vertices and therefore has an order of 4. The degree of the top vertex is 2 because there's 2 nodes joining to it. The second example in the middle has 2 nodes or vertices, therefore has an order of 2. The top vertex has a degree of 1. The third example has 6 nodes or vertices, therefore an order of 6. The top vertex has a degree of 3. From now on, I'll just refer to nodes or vertices as nodes. If the graph is undirected, you can move in either direction along the edges between the nodes. A network is undirected if the edges have no arrows. You can refer to these as undirected graphs. Edges represent the relationship between entities or things on an undirected graph. Examples might include friendship, data connections, time to complete, or distance. Example 1 here has 4 nodes and 6 edges. When 2 nodes are linked by more than one edge, they are referred to as multiple edges. Example 2 here has 2 nodes and 2 edges. It also has a loop, which is an edge that starts and finishes at the same node. Example 3 here has 6 nodes and 10 edges. A simple graph is one in which there are no loops or multiple edges. If a graph is directed, you can only move in one direction along the arcs between the nodes. A network is directed if the edges have arrows. These can be called directed graphs, but they also have a special name called digraphs. The relationship or connections on a digraph are called arcs. Some include timelines, water flow, or one-way roads. Here we have the same examples that we saw on the last screen. The only difference is the connections now have direction, and therefore they are called arcs. The first example has 6 arcs, the second 2 arcs, and the third 10 arcs. In a connected network, it's possible to travel from every node to every other node by following the edges. Here we have an example of a connected network. Notice that you can move from every node to every other node by following the edges. This example is a connected network, but we also refer to it as a complete network, where every node is connected to every other node directly by an edge or an arc. These are edges in this case. In a disconnected network, it isn't possible to travel from every node to every other node by following the edges. Here we have an example. The entire thing is a network, but it's not connected. Therefore, we call it a disconnected network. A path is a connected sequence of edges or arcs showing a route that starts at one node and ends at another. Highlighted in red here is a path through the nodes A, B, F, C. A circuit is a path that starts and ends at the same node, highlighted here in yellow. We have a circuit that goes through A, B, F, E, and then returns back to A. A weighted network graph is one in which the edges have been given numbers. These numbers can represent anything such as time, distance, cost. In our examples here, they're identified in green. The length of the edges or arcs generally are not drawn to the proportion of their weight. You'll notice in the examples here that the weight given could represent a number of things, and it's not proportional to the length of the edges or the arcs. Edges in the left example, arcs in the right example. A spanning tree is a graph that has only one way of getting from one node to another. A spanning tree is a set of edges that connects a network but has no circuits. It's usually a subgraph of another graph. Which of these do you think might be a spanning tree? The first one, this is a spanning tree because it doesn't have any circuits. The next one, this is not a spanning tree because it has a circuit. And finally, this last one, it's not a spanning tree because it's not connected. We can use weighted graphs to help find the smallest tree that joins all of the nodes. This is called a minimum spanning tree. This might help us find the lowest cost of connecting all of the nodes or the shortest distance. Let's look at a problem. A network has 8 nodes and is connected. Find the minimum number of edges. Remember, in a connected network, it's possible to travel from every node to every other node by following the edges. Start by drawing the nodes. Sometimes we may have to rearrange them to find a solution. So we're drawing in our nodes. We need 8 nodes. Now we've drawn 8 nodes. Now we draw in our edges. And in our example here, we end up with 8 edges. I think this can be rearranged to form a network with a smaller number of edges. If we move one of the nodes into the center, and we connect all of the other nodes to that node through the edges, we get a network with 7 edges. Therefore, the minimum number of edges is 7 when this network doesn't have to include a circuit. We're often given information in a table or as a list or as a verbal description. We need to use it to construct a network to accurately display the situation. Let's construct a network to represent the distance between shops A, B, C, D, and E in a shopping mall. So we know shop A is 45 meters from shop B and 15 meters from shop E. So we draw in shop A, and we can draw in shop B and shop E. We'll add the weight in once we've drawn the graph. Shop B is 25 meters from shop C and 33 meters from shop D. So we can draw in shop C and shop D. They both connect to shop B. Finally, shop C is 55 meters from shop D. So we connect those shop C and shop D. Now we can put the weights in of the distance between the shops, and we've finished our network graph. In this example, we don't know the direction. You can assume that people can travel on roads both ways. Therefore, we use edges without arrows in this diagram. Notice the length of the edges are not to scale, and they don't need to be. In this unit, we use what is referred to as the word algorithm. You may have heard it before. It sounds technical, but it really isn't. An algorithm is a series of steps that can be repeated over and over until a certain condition is met. Computers are really good at performing algorithms, and that might be why you've heard the term before. We can apply a number of different algorithms to networks in order to solve problems. In this topic, we'll look at a number of different algorithms. So in summary, in this video, we've looked at what a network is, the application of networks, graph theory, the terminology we're going to be using throughout the unit, types of networks, and what an algorithm is. Thank you.